you're going to do practical 6. Sorry, your movement today is a bit slower, right? Have you done practical 5? Finish it? Practical 5?
Yes.
Done this part already, track the development plans and also all of that. Done with that. Okay, so we're going to do MPI today, which is message passing interface protocol. So we've got several options in order to do error computing. The first one is what we've learned, OpenMP or OMP. And the second one is CUDA using GPU. And this is another way to actually do error computing using message passing interface. Okay, so what's different between the two? Okay, here I only compare with OpenMP. We try to compare with CUDA as well. So CUDA is using GPU. So OMP, most of the time is using CPU. Yeah, but I think the latest version, I heard they also support GPU as well right now. That means when you write the code, you don't have to change anything. It will check whether you got the GPU, and then you send some to the CPU, some to the GPU, and then process it using the same code. Okay, so you don't need to know whether you have GPU. You'll go and find out it yourself, and then use the GPU. And one thing good about this OMP is if you support the GPU, most of the time you will not only support NVIDIA, you can support AMD, whatever GPU they are. Because this GPU, they are not compatible. They are proprietary, so the interface is different. The way you program is also different. The machine language is also different. So OMP will handle it for you. Okay, if you use CUDA is only supporting NVIDIA. So there's a disadvantage. But the advantage of using CUDA is you have better control. Okay, because it can go very low level. Whereas OMP you might not be able to get too low level. Let's say you want to do some tweaking, you might not be able to do it using OMP. You might be able to do using CUDA. So the last one that we learned here is MPI. So this message passing interface is another protocol. This two here is using a single system. Single system, that means you got a computer system, and then that computer system might have multiple cores inside a single CPU, or you might have multiple CPUs, like IBM mainframe. They might have multiple processor chips on the system. So OMP can take advantage of all that, but it must be in a single system. Whereas this one can support both. It can support single system, but it also can support distributed system as well. Okay, because the way they communicate with one another, they use message passing. Okay, here they don't use message passing. This one is shared memory. Okay, so whenever they want to communicate with one another, they use a shared memory to communicate. Okay. Whereas on the distributed system, there is no shared memory, right? So one computer has their own memory, the other computer has its own memory. You're not able to share. So you cannot use a shared memory system or shared memory way to communicate. So MPI use another way. They use message passing. So this message passing is just creating a message, and then you can pass from one computer to the other, maybe using network. Okay. Okay, the disadvantage is shared memory, you put the data inside the memory, and then you just pass the pointer to the other thread or the other process. That pointer, you don't have to duplicate this memory. You have a memory pointer pointing here, right? So the thread actually put the value inside there. Once it wants to pass to the other thread or the process, you just pass that pointer. It does not need to create another memory and then copy over. MPI is different because it's a PC and then there's another PC here. It has its own memory, right? So there's no way for you to share the memory. That's why they have to pass the message. So what they do is, from the memory, okay, you create a copy. That copy is the one that you send over. Okay, you create this copy, which is a message, contains data, pass over, and then you store it inside this memory. So you got two copies here. Okay? And this passing here, it can be very slow. So that is a disadvantage. But the API, because it's a distributed system, that means you can let multiple computers to join and solve the problem. Here it depends on how many GPUs here, right? Let's say for example our NVIDIA GPU, maybe up to 2,000. Okay? Maybe less than 2,000 cores. CPU maybe 4 to 8 or maybe to 16 only. You normally don't have so many cores inside the CPU. Or if you have multiple processors like IBM mainframe, you might have this number of processors. Okay, maybe multiply with another 4 because it has multi-core. So basically that much of processing power that you have. Whereas in the MPI, because it's distributed, you can connect as many as you like. Okay, it does not need to be in this room. It can be anywhere in the world. Okay? So maybe your cluster is in Malaysia, some cluster is in America. Okay? They still can share the workload and solve the problem. Okay? So message passing, if let's say your data is, your problem is very huge, and you need multiple processors to solve the problem, then message passing is one of the best solutions. Message passing, if you have seen, or maybe you have heard before, SATI. Have you heard SATI? SATI is a non-profit organization where they actually scan the signal in the sky just to look for whether you got extraterrestrial signal that coming from the sky. Basically, just to find out whether there's ET in the sky or not. Okay, so basically, what they do is also using this multiple computer distributed all over the world, and then they take this signal that they scan and then pass to all this computer. Each computer will scan because the data can be in petabyte, quite a lot of data, because they scan the whole sky, right? So they send to a computer, and each computer will work on a small part of it just to find out whether there's any pattern in the signal, and then it will trigger the headquarter or the person who is actually managing it to find out, okay, this part here, but one particular constellation we find there's some signal. Okay, and most probably the signal might come from a distant galaxy, so they might want to do further research on that, then they can dive deeper. Okay, so one is SATI, the other one is related to medication, drug discovery or whatever. So they also need computers to actually do the protein folding. For example, we know the composition of the drugs, but how does it interact with other molecules, for example? This is something that they do not know, but they can simulate it. So what they do is, because the drugs, the molecule, when they fold in certain way, they interact with molecules in different way. Okay, so they have to try in different using a model, try in different kind of configuration to find out whether this drug is effective on what kind of diseases. Okay. So they use computer to do this. So this is basically using trial and error because we don't have the full understanding of how the molecules interact with one another. But they can create this chemical or physical model of it. So our computer is going to take some portion of that model and then simulate it. If we discover that it is effective in a certain way, then that result will be taken. Okay, so it will require quite a lot of computers in distributed manner. Okay, but of course, in this case here, if you sign up, meaning that you are giving free your processing power, which is unused one, to them to use it. Meaning that if I sign up, if my computer is not busy because I'm not using it, then it will retrieve the information from this organization and then do the processing background. Okay, so basically they are using your processing power for free. Okay, but of course for specific purpose. Okay, so that is distributed system and how it is used in the past and also now. Okay, so what is the differences in terms of programming? OMP, you have to add commas to existing program. So basically, you just change minor things on it. If you use for reduction, you don't have to change anything, just put the comma inside there. But of course, if you use other comma, you might need to change the program still. But if you use specific comma, you don't have to change your existing program at all. Whereas in MPI, you have to rewrite it. There's no way for you to use the existing one and hope that it will work like this one. OMP give you two choices. Okay, you rewrite the program or you use the for reduction, for example. Okay, in order to simplify the program. But MPI no, you have to rewrite the program. Okay, OMP, the compiler runtime system arrange for the current situation. And for MPI actually is also done by the MPI itself, but then behind the scene, it has to explicitly move the data around. Here you don't have to move the data. Okay? And OMP rely on shared memory, so it's fast. This one rely on network, so it's going to be slow. So that is the basically the properties of this OMP and MPI. So what we want to do now is actually try out to experience how MPI is used. If you learn, you see that they are kind of similar. The way they program is kind of similar. Just that we have to learn the libraries. Okay, MPI, unfortunately, this is not pre-installed inside our Visual Studio IDE. Unlike OMP, it's already pre-installed. This one we have to install it manually. Because it's installed manually, we have to do a number of configurations, so it's a bit tougher. Just a few steps, I think 3 steps. Okay, here is a link to this driver and also the SDK. We need both. Download it. Please follow because otherwise you'll be lagging behind because there are a number of steps. You follow because there's some exercise for you to do. Okay, download this. There are 2, quite small. Together it's about 10 megabytes. Okay, one is SDK where we use C++ to do the MPI. Okay, the other one is actually a program to start the MPI process. Okay, so you need both. So now, then we get downloaded. Okay, there are 2 files there. You can install in any order. Install the SDK first. This one is going to be used by our Visual Studio IDE in order to compile together with our C++ code. Actually, MPI is not only actually it doesn't target in C++. I think it is written in C because it also supports C, but of course our program is going to be C++. C++ is very compatible with C, so it should be able to compile normally. Once that's done, run this Microsoft MPI setup, which will install the appropriate program in order to start. Okay, please check this. Look at this folder because later on we need to go to this folder in order to retrieve, or not retrieve actually. We need to copy the path for the IDE installed already. Now we go to our Visual Studio. You use the link that I give here because I changed the link to the latest version. The latest version is this one. Check the internet. 10.1.3 is the latest. It was released in 2023, I mean last year, June. But this is the latest. Okay, and create a new project. We are not doing any project, so console app. Choose C++, console app, P6, P6. Okay, so they are here, and then we need to do the setup. Okay, you need to do the setup for every project. So I'm creating a new project, so I have to do setup. Meaning that if you create another project for MPI, you have to set up again something similar for that other project. Okay, so this project, right click on P6, go to properties. Actually, if you miss what I mentioned just now, you can go to here. It actually tells you what I'm going to tell you now. But I'm going to go quickly because I'm not going to go through this one-on-one. Okay, but if you miss what I say, please go back to this and then follow this document. You should be able to get the same configuration properly. Okay? So the first thing is we're going to set up the include path. So the include path is C additional include directories. This allows us to include this MPI locator. When you include MPI, you type MPI data. So it needs to find out where to get this data. You can see there's a wavy line there. It indicates that you cannot find this. So we need to provide the path. So the path is should be placed inside here. And let's get back to our register. I asked you to remember, right? Actually, it's easy to find out. It's either in here or here. I guess it's here. Okay, Microsoft SDK MPI. So it's this, and then you see this here. So copy this one. So program files x86 Microsoft SDK MPI include. You copy this and then paste it here. You click OK. So that's the first step. The second step is to include the library path. So there is the header only. So right now you see the wavy line disappear. Because right now it knows where to get this header file. Because we point to that folder, right? So it's able to find. If you open up the folder, you see MPI.h inside. Okay? So the next thing is, this is just the header. The header is just giving them the constant and also the function profile so that we can use our we can check our program when we compile with the MPI libraries. But then we still need the code, the source code. Now the source code is already pre-compiled in the SDK, which is located in the library. We need to tell the IDE where is that MPI source code. It is just the header file. The source code is somewhere. It's pre-compiled source code. We should call library. It should be at the linker. And then go to I think it's input, if I'm not mistaken. No, it's not input, general. Linker general, and you see additional libraries here. So this is to tell where is the source code in machine language, which they call a library. And it's also here, it's around here actually. Now I'm in include, we go up to the parent and you see library there. So here is the source code in machine code. And we're going to use x86 because by default our IDE is x86. I suggest we use x86. So this is the library that is going to be used. Most often it's the first one. Okay. So we need this part, just copy this. So this one is program files x86 Microsoft SDK MPI library x86. Okay. Now make sure if you use x86, here must be x86. If you are using x86, then you have to go up again, back here, to choose this part. Okay, you can see the same library there, but right now this library is x86 library. Okay, so we get that here, copy this, and paste it here. Okay. Okay, the last step is to tell which library, because inside the park there's so many libraries, like 3 altogether. We're not going to use these 2 at the moment. We're going to use the first one. So this first one, the name is this, just copy the name. And then we go to input. Under the input, here you see there's an existing text there. Don't delete it. Okay, just keep it there, don't delete it. Paste it right in front. Okay, and then put a semicolon. If semicolon is this, just in case you don't know what semicolon means. This is semicolon. Semicolon, okay? Dot and a comma. This one is colon. Okay, this is the semicolon. And this one is colon. Okay, the semicolon is just after that name, and Microsoft MPI.lib semicolon. You have to put the semicolon. If you don't put, then it will not be correct. Okay, make sure that you put the semicolon there. Okay? So what I mean is Microsoft MPI.lib semicolon. That semicolon is there. Alright. Okay, if you miss what I said, those will actually come later. Just follow this text here. The text here actually give you very clear guidance already how to do it. I'm just doing this demo in front of you because you might want to see me how I did it. Okay, so once that's done, the pre-setting is done. Now we are ready to try the first. Actually, it's just say for example. You can try together with me. I'm going to copy this code. Click on it. Go to the drive. Okay, this is the first program, very simple one. Okay, you'll come back to this program again and again because maybe you'll start somewhere later on. Refer to this program because this program is a working program. Okay? Make sure that you come back to this program again later. Because as I go along, there's an exercise, and that exercise, if you don't follow what I say, you refer to this program. Okay? This program is a working program, and then learn from here, and then apply this. What you did is you learn from here in the question later. Okay, so the first thing first. I'm going to change this. I'm not going to call MPI name. I'm going to call MPI name. Okay. And then copy this down below here. The main is down below. Okay. Copy exactly, including this 2 input parameter here. Normally our main don't have the input parameter, right? Most of our main I never put it before. It's empty. But here, there is something there. Okay. Okay. Why we need this? Because you see the MPI init there. That MPI init requires it passing through information. The information is this too. Okay. We can pass now, but I suggest not to because I'm not sure what it's going to do with it. It's better to pass in whatever that the operating system is giving you. Okay. So the operating system, when you start the program at the time, the operating system can tell you some input, okay, and it will give you the input in it, right? And then the first parameter is to tell this main how many input that you have there. Okay, you got 2 input here with 2, 0 here with 0. Normally it's 1 like this. The first one is always the name of your program. Okay. So the input that's
at least one, which is the name of your program. In my case here, I call it P6, so the name will be P6, and here will be 1. Okay? The rest of the input will be additional input that you pass into the program, and maybe I'll show you later how this tool is used. At the moment, this tool is used by our MPI init, so we need to pass it to it. Okay? So how do we pass the MPI init? We pass to this MPI demo here first. We pass in here, and then this MPI demo is going to use it and pass it here. Okay? So let's call MPI demo, and then just pass in this tool. Okay, you don't have to worry at the moment what is the content inside there. Just pass in. Okay, so that this MPI demo can pass it to the MPI. Okay. There is some kind of rule that is in place in order to use the MPI. Before you start using the MPI, you have to put MPI in it. Okay? After you put the MPI in it, then only you can use any of the MPI functions. Right? So the MPI functions is something like this. Okay? Finally, once you're done with the MPI, you have to finalize it. That means you're going to clean up. Okay, finalize means do something. So you have initialize first before you use. Then after that, before you return, finalize. Okay? So these two steps is important. You cannot miss it. If you miss the first step, you will not be able to run. Okay? Because if you start, if you run using the MPI program to start it, you complain that there is no MPI, okay, you will not progress. Okay, so this part important. And it takes two inputs, as I said, and this input comes from here. And actually this one comes from here. And this one comes from here. And these two actually come from the operating system. Okay? So once that's done, you can run the program, because this program is actually a working program. Okay, so when you run, you see hello world. Okay? First line. The second line, hello world from process rank number 0 from 1. So let's see what this means. Okay. Okay, when I start the program, unfortunately, this IDE, when you run the program, you run using, actually run the program directly. So when you run the program directly, it's just like normal program. It's going to run this program as though as there is one process. Okay? So that's why here is 1. 1 means you are one process. What is the ID of this process? Is 0. So let's have a look. How does it know 0 and there's only 1? Okay? Now look at the program. The first line, see out hello world. That is what this hello world is. Okay? And the second line is basically the variable, rank and non-process. Two of them are initialized to 0. And then MPI init to initialize the MPI. And here, this tool is something similar like OMP. Remember, we always use two functions at the beginning, where you find the thread ID. The thread ID is similar to our rank here. So MPI call it rank. Okay, OMP call it thread ID. Basically, it's the same thing. Right? So rank and thread. Actually, here it's not thread. We call it process. So process ID is rank. Okay. And then the second one is the size. So size is the same as the number of threads in OMP. Okay? Get thread number. Okay? When you get thread number, it's the same as MPI com size. Basically, you just get this number of processes that is running at the same time in parallel. Okay? So when I run the program, first you get the ID of this process, and the ID happens to be 0. Okay. And then the number of process is 1, because I start this program by running this P6 directly. That's why you see 1. So how do I start with many more process? I cannot run this program directly. I have to use the MPI program. It's called MPI exec. Okay, this program, we installed it just now. We have two programs, right? One is SDK, the other one is MPI, Microsoft MPI setup. So inside the setup contain this program. We need to use this program in order to create many more processes. Okay, so if we run directly, you create only one. In order to create more, you have to use this to run this program. Okay, so this will initiate the process to run this program. Okay, now it will be the same like OMP. So let's have a look at all this. This tree, yeah? Okay, QDA, you have one code which is the kernel. Okay, and then when you run the kernel, you tell where the kernel is and you start. You initiate the kernel, right? Okay. And of course you have to configure the GPU first, like how many threads inside the block, how many blocks inside the grid, right? So the GPU will assign threads to execute this same program. So you got single program here, but each of this thread here is going to work or process their own data. So data 0, data 1, data 2, and so forth, data n. Okay? So multiple threads running the same program because single program, but each thread is going to work on or process on different data. So single program, multiple data. Okay, so this time I'm going to touch on this in one of the lectures. Okay, so we've got single program, multiple data. Okay, the way the QDA works is like this: single program, multiple data. Okay, how about OMP? OMP is also the same. You have one program, and then you put the pragma, right? And then the pragma will start the pragma parallel, OMP parallel, and it start the program, start running the code, and you assign multiple threads to execute the same code. So it's basically the same thing: single program, multiple data. So because each of the threads is working on different program, different piece of data. Okay, how about this MPI? MPI is also the same. It's going to be running all of them. When I use this MPI exec, I'm going to tell MPI exec, please create, let's say, 4. Okay, minus 10 means I'm telling MPI exec how many processes I want to create. Okay, I say 4, and then I put P6 at the back there. P6 is the program that I want to run. Okay, this program here. So I put -n4 means 4 processes, run this program. And then you're going to assign 6 processes to run that same code there, which is basically the main actually, because the main is calling the MPI demo. So all of them is going to call this. Okay? And it's basically single program also multiple data. So all of them are actually a single program, multiple data. Okay? But of course there are many different kind of parallel computing. Okay, we have single program, single data. Okay, this is our old computer or old way of running program. One program, one data, right? Single processor, single process, single data. And we have a single program, multiple data, which is this one. Okay? And we can have also multiple program, single data. We also have multiple program, multiple data. Okay? So basically we have 4 different types. Okay? The type that we are covering for QDA, OMP, MPI, all of them are the same. All of them is actually this. Okay? Single program, multiple data. Okay, how about threads? Threads library that we learned in P5. Yeah, P5, the last part of the P5. Thread libraries. Okay, the thread library is a thread.h. This is the library. don't get confused with the thread. The term that I use there is also call it thread. But this library here is a thread library, and we see that when we start the thread, we can assign to different program, right? So basically, it's multiple program. It's not single program. It's actually multiple program. Okay, but thread is very flexible. Actually, thread can do all this. If you assign this multiple program, then it becomes multiple program. Okay, if you assign all of them to run single program, then it becomes single program. Okay, and that depends on the program inside. Yeah, if your program inside work on the same data, but multiple program, then multiple program, single data. Okay, but if let's say if this is a multiple program, multiple data, that means each of the program will work on different data, then it becomes multiple program, multiple data. Okay? Alright, most of the problem are of this type. Single program, multiple data. That's why a lot of them are using this model. Okay? A lot also is in MPSD, which is multiple program, single data, but majority of our problem is of this type. Okay? In the past, we always use this, but right now we're moving into this. Okay? Because we got many more processors, so we can use single program and then work on different pieces of data. Okay? So let's say, for example, some of you are doing image processing, for example, right? So let's say, for example, this is the picture that you want to compress. Okay? So when you compress, basically you use the single algorithm to compress it. Okay? So you can have a choice. You can use one process to compress the whole picture. Okay? Or you can chop it down. You can chop it down like this. Maybe into this size. And then you let track number 0 or process 0 only process or compress this image. Okay? Track 2 is going to compress. So track 1 is going to compress it. Track 2 is going to compress it. Track 3 is going to compress there. Track 4 and track N. Okay, we continue on. So you can see that each track is actually having their own data to compress. But the compression program for all the tracks is the same. It's the same program. Isn't that a single program, multiple data? It is, right? Okay? And of course, if you have more track, your data to process for each track is going to be smaller and smaller, shared among all of them. So you can see that each track is going to run very fast, right? Because they only process a little bit of it. And imagine you got GPU, you got this much of cores. So you can spread out 2,000 cores to do this. So it can be extremely fast. Okay? Compared to single core, okay, this 2,000 cores is going to be theoretically 2,000 times faster. Okay? So if let's say your compression is very complex, then it can be performed very quickly as well. Because why? Even though it's complex, but the data size is small. Unlike this one more big picture here, maybe it's high resolution, so the size is going to be very big. Okay, so one example is this. The same thing for, let's say, for example, you do CT scan. So what they do is they chop down your actually it's not chopping down, they just send X-ray through your body in lateral manner. So when they scan, they can actually look into your body slice by slice. Okay, so each slice maybe is only processed by track number 0. The second slice by track number 1. So basically, also single program, multiple data as well. Right. So every slice is done by a particular process. So it can be very fast. Okay, imagine the processing for each slice can take several minutes or maybe hours. And you've got so many slices to do. If you assign to multiple threads and multiple process, it will be faster. Okay? So most of our problem is of this kind of problem. The best problem is actually this. Multiple process and multiple data. Why I say this is the best? Because if you look at all of them, there is some shared data. So one track have to wait for one another. If they have to wait for one another, that means, or they are sharing some data, that means you have to do new text. New text means critical region. Critical region means somebody needs to be blocked if somebody is touching the data, right? So in that case here, there has some dependency between the processors or the thread, and therefore it can slow down the system even though you have multiple threads because they have to wait for one another. But if your problem is of this kind, then it's the best. Why? Because most of the time your data is not shared. You've got multiple data, most of the time it's not shared. And then you've got multiple programs that is actually not shared as well. Okay, they are independent of one another. Okay, so but unfortunately our problem is not of this kind. Okay, very rare is of this kind. Okay, the majority is SP and D. Okay, this actually is kind of similar to what you have learned in maybe computer organization and architecture. You learned this subject before, right? Huh? Somebody say yes, yes.
Foundation.
Huh? No, foundation. I think diploma or the first year in your bachelor degree. Something to do with the computer organization and architecture, right? COA or something like that. You know that? Okay, if you learn, you might have heard of this. Single instruction, single data, SISD. Single instruction, multiple data, SIMD. Multiple instruction, multiple data. Or multiple instruction, sorry, here is single data. And this one is multiple data. Have you heard of this term? If you learn COA, you should be able to recognize this abbreviation. Or maybe SIMD. Okay, actually if you learn that, there are some similarities between these two because you can see here, the only change here is the program and instruction. Okay, the difference here is, this one is you're looking at the CPU. Okay? Because CPU run the instruction, right? Here we're talking about program, so we're talking about the language, okay? Language level. Okay? This is a CPU level, lower level, but basically they are the same. Okay? So basically, if you learn SIMD, basically it's SPMD that we are talking about here. Alright. So because of that, we need to know that our program basically run the same program, but it might have different data. Okay? So you need to know there's some kind of limitation. If you want to run multiple programs, multiple data, then you have to make some changes. Okay, there's a way to do it. It doesn't mean that this architecture cannot run all this. It can run in this way as well, but naturally it's this. If you want to run in this way or that way, you have to put some code inside that in order for it to run in this manner. It's not so simple. Okay, but naturally it runs in SPMD model. Okay, so come back to this. So what does it do? Actually, get the ID of the process, get the number of processors running, and then print out this. That's why you see this value here, rank 0. Okay, now in order to run MPI exec, okay, if you go to here, sorry, you go to here, right click on this, open terminal, and you will open up a PowerShell for you. And you can type in MPI exec. Okay, okay. In your case, I'm not sure whether you see this. Most probably you see an error. Do you see an error? If you see this, that is not error. This one, because I already set up. Actually, because I did not switch on my computer. Yesterday I was doing it and was running the whole day. If I switch off the computer, it will be error. In your case, because you switch off computer, do you see an error? Or you see this? Microsoft MPI startup program. Huh? Anybody here see an error?
So, how to open?
Right click on this, right click here, and then go to open terminal. Then this one will come up. Okay? And then you type in MPI exec. Okay, because my computer is already set up, configured properly already, I don't see an error there. Right, I expect to see an error. I don't see the error. Anybody here see an error? You see an error? Okay, those who see the error, because I think maybe your computer was not shut down. I believe my computer is not shut down. Because I'm able to trigger. Okay, the one that you see an error is because your PowerShell is not able to find this MPI exec program. You cannot find it. So you need to tell PowerShell where this program is. Okay, in order to do that, okay, follow this. Follow the road. Those who cannot get it working. Click on this. Type env. Okay, actually it's all here. I will put it up here. You go to Gmail, Google Chat. Okay, there. This one. Okay, I will show to you. If you miss what I said, just refer to this because I already posted in Google Chat. Okay, this is what we need to do. Go to the window icon, type env in the search bar, and then follow this step. Okay, click on this icon, type env on the search bar, and then click on edit environment. Okay, and then environment variables, click on this. Right, and then follow this path, double click on it, so will come out. Okay, and then what you need to do is just add a new path here. So the path is going to be the path leading to the MPI bin. Okay, so how do I get there? You go to your folder. Okay, you have to go up until C drive. Okay, the MPI exec is not installed here. Install here, program files. Go to program files. Go to Microsoft MPI. Go to bin. Okay. Unfortunately, it goes into a different folder. Just now was program files x86. Now it's program files only, no x86. Program files, Microsoft MPI bin. So you can see MPI exec. So you need to copy this up and put it into this environment so that the PowerShell is able to see it. Okay, so put new, paste it here. Click OK, click OK, click OK. Right? Now if you try again here, okay, you try again, and it still produce error. Of course, in my case, it will not produce error. But if you still produce error, but you already done that step just now, right? What you need to do is you have to refresh your Visual Studio. Close it first. Okay, close it. And then reopen it. Okay, close it first. If your PowerShell that is running, close all, including your Visual Studio. Okay? Including all the PowerShell's terminal that you open. Right? And then double click on this. Sorry. Then you come up here. Now, if you click, right click, go to open terminal, you are able to type this without any, it will not give you any problem. Microsoft, so MPI exec. So I made a mistake there, there's a C at the back. Okay, just one example. If you, okay, I purposely made a mistake there. Okay, I not put a C there, but this is the error that I expect to see just now. Okay, if you cannot find the file, then it will not recognize. Okay, but because I think I did not switch off my computer, so it remembers the path that I I configured earlier on. So I'm able to see where the MPI is at. Yeah, anyone here still got problem?
The environment variable to add user of system to need to add the user variable is the environment variable.
Yeah, Google this. Click on this. You see the picture there. Alright, I know that you're going to miss it, that's why I purposely do this and send it to all of you. Okay, first step, second step, third step. Okay, follow that. Okay, done? So once done, now what we need to do is just execute and tell how many process. You put one here, that means one process. No difference from running it directly. Okay, you use this because you want to create multiple process to run this program. So you put add 4. Actually, is here, is written there. Here's the one. The name here is actually P6. Sorry, P6. Right? So you copy this and then paste it here. Paste it there and then press enter. Okay? Then it should. Okay, you see an error there. It says failed to launch P6 because we are at the wrong folder. Okay, when you open the terminal, it will give me, it will start with this, start from this folder. And my program P6 is not in this folder. Where is my program? My program is, okay, let's copy this. Let's see where the program is. Copy this whole thing. Okay, and then paste it here. Okay, my program is not there. My CPP file is there, but I'm looking for the executable file. The executable file is not here. It's actually one parent up here, and then go down, X is X64, and then go down further, debug, and it's here. This is the program, P6. It's actually in this folder. So copy this, type CD, change directory, and then paste it. Press enter. Use CD, paste the folder that you copy just now, press enter. So it should be inside this P6. Just now was P6, P6, right? Actually it's inside P6 X64 debug. Okay, it's inside it. Okay, if you type dir directory, you list down the program. So the program is there, P6. You can see that? P6.exe. So this is the program that we want to run. Okay, so right now we can run the MPI exec. Okay, and then we give you this result. Okay, MPI exec minus n space 4 space P6. Okay, because there are 4 processes, that's why you can see hello world 4 times. Okay. And then hello world for process rank 4 times as well. But here, each process is going to print out its own rank, which is their own ID. So 0, 2, 1, 3. Okay? And how many processes that is running together here is 4. Why? Because I put 4 here. So there are 4 processes. So the process know how many bodies that is running together with the process. Okay? And then it also can find out its own ID, the process ID. Okay? So if you play around this number here, you can see different number. If I put 8, now it will be 8. Okay? Sorry. Okay. So I got 8 here. 8 hello worlds, and then another 8 hello world message again, but with the ID number 5. 1, 2, 7, 4, 0, 3, 6. Okay, the order, as I said before, is not in order because it sees who is faster. So it puts that process 5 is very fast, so you're able to print first. Okay? And then followed by 1, followed by 2, followed by 7, followed by 4. And 0 appears here. So the 0 is quite slow. Okay? So you can see its own ID, knows its own ID, and is running this one is running in parallel. okay, or some in concurrent manner, but most of it is in parallel, depending on how many cores that we have. Okay, we can find out later how many cores that. Now, if you look at the MPI exec just now, there is some example that is shows to you here. Okay, see the example there. Here, this is the program name, and then we use auto for earlier on. So we are using this style. There's a second style at the bottom here. Okay, and the second style is actually. Remember I mentioned to you that the MPI is not only running on a single system, it can run in the distributed manner. Meaning that you can try using this MPI in your assignment. And I hope that some of you will try MPI. What you do is you can start a number of PC, okay? And then you register the host name. Later I will show to you where to get the host name. So each one of the computer will have its own host name, okay? And it has its own IP address. So you create a file containing the host name and then the IP address, okay? And then you can start the MPI exec, start the program, and then you tell how many workers that you want. The workers will be the number of processes, okay? And then you pass in the file contains the host name, and then you go. The MPI is going to contact all the processor, all the PC, and then instantiate the number of processes that you want, okay? And then you send by message passing the program to all the computers, and then they will run at the same time. Okay, so this is running distributed manner using message passing, okay? Which currently GPU and OMP does not have this kind of capability. Okay, so I can tell which cluster of computers I want to use. So if let's say you've got a very big cluster, let's say 100 or 2,000 computer, you can actually use the MPI, and then MPI exec is going to help you run the program and also communicate by using message passing. Okay, so our program is going to be like the same, whether it's on the single computer or distributed manner, it doesn't matter. Our program is the same because whenever we communicate, we use message passing, right? So automatically, it will go through the network if it has to go through to a different computer, or the message passing is within the computer itself. It doesn't matter, okay? Because the program is exactly the same for through the network or in the same system. Okay, so this program is actually a working one. Please refer to this when you do the exercise later. Refer to this. Okay, let's move on. Okay, this one is what I mentioned just now. I'm going to skip it. And here, I actually show you some pictures. So imagine that this is different computer, and each process is going to run on each of the computer, and then this is the same program that everybody is running. Same program, that same OP there. Okay, that's why it's single programs and then multiple data, because we might have different data on different computers. Okay, so you can see MPI exec is actually do in the background. This using message passing, pass the program, even the program, not just the data, even the program is passed along to the PC to execute it, right? So you might have one process running this, or you might have several processes running at the same time on the same PC. Here it shows only one. Okay, so you can do something similar. Of course, we have to pass the correct information here, telling MPI exec what to do, how to distribute the data. Sorry, how to start the process and where the process is starting, and how many computers in a cluster that is working together to solve this problem. Okay. Okay, let's go to exercise question 1. Now use the command MPI get processor name. Remember, I mentioned to you that the MPI needs to know the host name. my computer has a host name, your computer also has no host name. So we need to tell API which host name is within the same cluster, right? And then it will contact this computer using the host name, and then of course deliver all the necessary data and the program to run the program, run in the process. Okay? So how do we extract the host name? We extract the host name using this name. Get processor name. So let's copy this because here it does not tell you the function prototype of this API get processor name. Okay? We go to the first one and it tell you how it looks like. It return integer, takes it into parameter. The first parameter is a pointer to character. The variable name is name. So basically we know that there's a name, the name of the processor. And then the second input argument is a pointer to integer. Okay, the variable name is result. So we know that this is going to hold the address of the result line. This is going to hold the name. Okay? It's kind of funny. Actually, we are not passing in the data. We actually extract the data out. Okay? But what you pass is actually a buffer. You pass in the buffer containing nothing. Okay? The buffer is empty, and you expect this API get processor name to put the name inside it. Okay? And then this function also will return how many characters inside the name that he has already put. Okay? If let's say my name here is host1, let's say host1 is 5 characters, right? So it's going to put 5 inside this result name. Okay? So we know that the size of this length, the name. Okay? So I'm going to do this exercise. Okay, I'm going to do this exercise by putting it inside here directly. Okay, I cannot put before the MPI init, I have to put after. Okay? Now I need to put in the name, the host name, the name by it, and the bank. And I'm going to pass in the address and the address. Okay, now let's look at the host. How does the host name look like? It tells me it's a character. Okay, just now we saw it's character, right? So host name must be character and it's array. Okay, what is the size of this array? The size of this array is cannot be less than this. Okay, so I need more than this or the same size as this. This one is defined inside the API calculator. I'm not going to find out how many. I'll just assume that they know what number to put there. Okay, so I'm going to put it inside here. Okay, the max processor name. Okay, and then integer name line. Okay, and I pass the address. Okay, here I don't have to put the $sign, sorry, ampersand in front of the host name, because host name is actually an array. Whenever I use the host name, actually that host name is the address array. So I don't have to put the ampersand. Alright? But what actually I'm sending is the address of this host name. Okay? Because as I said before, array, the name itself is already the address. Okay? Now the second one, name length. Name length is not an array, it's actually an integer. Okay? But I need to pass the address of this name length. That's why I have to put ampersand in front. Okay, the first one I can skip, but the second one I cannot skip. Okay, the second one, the name length. If I put name length, it pass the value inside the name length. But if I put ampersand, I'm passing the address of this name length. Okay? Why do I need to pass the address? Because if you look at the MPI get processor, okay, the result length is a pointer to integer. So it's actually holding the address of the name length that I passed. him. Okay, so I pass the address to this pointer, right? And it's going to write into here the number of characters of my host name, and it's going to write my host name inside this, so that I can print. So let's print it out. Let's print out here. 300 host name. Run program. So my host name is called desktop. Blah, blah, blah. Okay, and how do I know this is correct? Actually, you can go to setting. Here you go to about, and you can see the name up here, okay, on your system. Then you go to setting, and you go to about, and then you will see this. This is the name that is what is printed up here. Same as it. Okay? So this is my computer name, and your computer name will be different. Right? So the computer name is how we actually tell the API. Actually, API don't use the computer name only. You use the IP address. Later on, maybe in some example we can try. Running the API exec, but you're going to distribute to multiple programs using the IP address and also the host name. And then you run on different program, and then you accumulate the result back on the master program, computer. Okay. We'll do that later. For now, we are going to run on single system first. Okay. This one is going to print out only one, right? But if you run it here, then you print out multiple. Okay. So, and of course, if you click this button here, you will not run multiple process, right? You're going to use this. So how do I? It's going to be slightly different from when we program OMP. Okay, OMP we just press play, and then you do everything for us, right? So you're going to run multiple programs, multiple threads and multiple process. But here we have to do it manually. So how do I do it? You can do it by point and click. Go to build, click on this, check there's no error, and then go to developer PowerShell, and then type in this. And run. Okay. Okay, then only I run. Now you can see desktop. Host name is going to be printed 4 times. Okay? So if I make changes here, let's say I make some change here, I put not only this, I also put in the length, name length. Okay? Okay, you don't have to run, click on this. What you do is you press Ctrl-Shift-D. Okay? Ctrl-Shift-D means build. Ctrl-Shift-D. Build, so you build for me. If there's no error, you just say build completed. If there's error, it show you all the errors. Okay? So I know it's successful. Then I can go and click here, and then run the program. And then it shows to me 15. Okay. Name length is 15 because there are 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 characters. Okay? So who actually put this name and 15 is the API get processor name. I pass in the host name, which is an empty buffer, and then it's going to write for me this. And then when it comes out, so when I print the host name, we print out the host name. Okay? And that function also will put in the number of length, the number of characters in this host name, which is 15. We're going to run inside that. So that's why when I print it out, it's 15. Okay? So this is not done by myself. It's just done by API get processor. Okay? So you can later on when you do different kind of exec, we can run on this computer, we can run on other computers, and then we can display who is running where. Okay, you can check which process is running on which computer. Okay. Okay, so with this, let's move on to the next exercise. And this time, we're going to do yourself. Question number 2. Okay, this is question number 2. Okay, let me go through a little bit of it first. And then what is expected of you. And then you try to solve the problem. Okay, this question number 2 is similar to question number question P3. P3 means is previous practical P3, P4, P3, P4. Actually, they also do this, right? It's basically trying to find the pi value 3.14 something, right? So we're going to solve this problem again. So we have solved this using OMP. I can't remember if we solved this using GPU, no? But now we're going to solve it using MPI. Okay? So the program is going to be given to you, which is here. Alright? Except that there's some empty statement there where you have to put in. If you don't put it correctly, it will not run. Okay? Or it will not run correctly. You have to put in the correct information in order for it to run properly. Okay? So let's have a look of the program again. So in order to find the pi, we need to integrate. And what we do is we chop it down into small pieces, right? Because if you want to integrate them, that means you want to find the area and integrate each area together. And here it can be quite a lot. It can be 10,000, it can be 1 million, depending on how big you want. Okay? The smaller the step, the more accurate it is, right? But the more accurate it is, the larger the number of this, and then you have to compute more. To compute more, that means slower. Okay? Now, in order to expedite or to make it faster, we distribute it to multiple processors and then run them. Remember what we did in the OMP? It's the same technique that we're going to use here. So we can have multiple threads running. Let's say we've got 4 threads. So we're going to assign this first strip to process 0, process 1, process 2, process 3, and then we start all over again. 0, 1, 2, 3, 0, 1, 2, 3. Okay? But of course, this strip number is going to be strip number 0, strip number 1, number 2, number 3, number 4, number 5, number 6, number 7, number 8, number 9, number 10, and so on. Okay? But then at the bottom here is the thread or the process ID who is going to compute this strip number 0. Okay? So we're going to use only 4 threads, so you're going to repeat, right? Okay? So you can see that process number 0 is going to do strip number 0, strip number 4, strip number 8, and so on and so forth. Okay? How about process number 1? Process number 1 is going to do strip number 1, strip number 5, and strip number 9. Okay? The same thing for process 2 is going to do strip number 2, and then strip number 6, and then strip number 10. Okay? So the spacing is actually the number of threads. So 0 and 4, and then 8. So it's 0 plus 4 is 4, plus 4 again is 8, right? If your process is 1, okay, the next strip that this process is going to do is 1 plus 4, which is 5. So it's correct, it's 5 then. So plus 4 again is 9, so it's correct, it's 9. Okay? So if you look at the program here, let's have a look. Here's what it does. Okay? We're going to copy this. not going to call it main, I'm going to call it with a different name. I'm going to call it calculate pi. Calculate pi. Okay? Yeah, I'm going to move this one up here so that it's clearer. And I already have all this, so I'm going to remove them. Except for STI Studio, so I need to do some changes because here STI Studio is using C printf. If I'm going to use printf, I'm going to use C out. C plus C out. Okay. So I have to go down and make some changes here. Whatever printf, I'm going to change it. Make it more compact. Here is one, the printf which I want to eliminate. So C out, empty, equal, and I pass it this, print out the size, and then print out this string here, and then I pass in this begins minus n, which is basically the time period taken to run this program. Okay, and then print this. Okay, and then print out pi, which is the result, and then finally print out end of line. Okay, so I'm going to do that. Yeah. So I replace just now with C. No change, I just still using print out the C. Okay. And remember I called calculate pi, so I'm going to call it here. Calculate pi. And the same thing, it takes in two parameters, argument s and argument us. Okay, I'm going to comment this out so that we're not going to see the exercise exercise of the time. Okay, if we look at the program here, this is the core program, and remember I was talking about this. Actually, it's doing that. Okay, so first we find the rank. Why does it need to find the rank? The rank is going to tell your ID. The process 0 should do strict number 0, strict number 4, strict number 8. So your rank is 0, so start from I0. And then you compute for strict number 0. So that equation here is basically multiplying. Multiply the y, find the y, and then multiply with this step. Okay? Multiply with this small step. Okay? And then you add into the result. So I would start with from 0 because process 0. Okay? Now the process 0 is going to do the next strict. The next strict number is 4. So that's why I plus equal size. And the size is going to be the size of your number of processors going to be run. Right? So our size is like 4, then it will be 4. So I plus 4. And you put back to I, so it's 4, right? Because 0 plus 4 is 4, which is correct. It's 4. So it's going to compute that. Then you move on to the next one. The next one is plus size again, which is another 4. 4 plus 4 is 8. So 0 is going to do strict number 8, which is 12. Then it continues on until the end. So process 1 will have its own partial result. Okay? Now process 1, which comes in, the rank will start with 1, right? So 1 is going to do strict number 1, which is correct. Because I, when it starts time, is the process ID, which is 1. So it's going to compute the strict, the area under this strict is strict number 1. Okay, and then I plus equal size. So I plus 4 is going to be 5, which is correct. Because strict number 5 is going to be done by process I. That's process 1. Okay? And then you plus 4 again will be 9. Plus 4 again will be 13. Plus 4 again will be 17. So on and so forth until the end. And once it's done, it's going to have its own partial sum. So each thread is going to have its own partial sum. Okay? So once the partial sum is computed already, you reach this point here. Okay? So each thread has its own partial sum, which they call the result. And one of the thread, or one of the process, is going to combine them. It's the same thing as what we learned before. We have learned reduce, right? For reduction, remember? So you take all the result and then you combine them, basically you're reducing the size. Okay? So when you add them up together, that process is going to be done by one process only. And we choose rank 0. You can choose any rank that you want. But here we choose rank 0. Why? The reason is so that you don't have to come back here and change the number always. Okay. How many process, minimum number of process to run? You can have as many processes that you want. Right? You can create 1,000 process. If you put MPI exact -n 1,000. So it'll be 1,000, right? Now, what is the minimum number? Huh? 1. It's correct. Otherwise, if no process, no need to run, right? So you need at least one process to run this program, right? If there's only one process, what is the rank? 0. Alright? So isn't that rank 0? You're asking that single process to do it. Okay? Now we don't choose rank number 1 because we do not know who is going to run this and how many processes that is going to instantiate, right? So we assume the worst. Assume the worst is one process only, right? Because you cannot put n equal to 0. You have to put 1 at least. Okay? So there will be always one process that is going to compute this. Right? And it's going to be rank 0. Right? So I think rank 0 is the best choice. Don't choose any other rank, choose rank 0. Because if you choose 3, if the person put n equals to 1, then your program is going to fail. Because there's no process 3. Right? Alright? Unless the person type n equals to 4, then you will process 3. Okay? So if you choose rank 0, is the safest one. Okay, so we choose rank 0 to do this job. And what does it do? It's going to reduce all the result into 1, which is going to be the sum. And then it will multiply with this to find the pi. And then print out. Okay, you print out the size, the number of processes, how many processes. If you create 4, it will be 4 there. And the time taken, how long it takes to compute this. And then you show the result. Okay, now you have to check the result. If the result is not 3.14 something, then you know that that is the wrong answer. And you must have done something wrong in the program. Okay? Okay, so all this program is, the processes is going to run the same public file, but it will be working on different data. Okay, remember I mentioned to you, single program, multiple data, because each process is going to run on different data, right? Okay, and then finally we choose one rank or one process ID to do the sum. Okay, now how do we sum it? It's the same as for reduction, and here we call MPI reduce. So let's go back to here, and this is where the MPI reduce. Okay, in OMP we also have for reduction, and we pass in, what do we pass in? First thing we pass in the name of the variable that you want to reduce. Okay, that's the first one. Second thing is the operation that you want to do. You want to add, you want to subtract, you want to multiply, or whatever. Okay, so you have to have these two information. Now in MPI reduce there are more, not only these two. Actually you have two here as well. The name is here, the name is inside here. Okay, actually these two is the name. And then the operation is here. But you also have this count, you also have data type, you also have root, you also have MPI count communication. Now, I want to explain this count first because I just want to mix the count. MPI count. Let's get back here first because otherwise I am not able to explain this MPI count communication. Now, if you look at the program that we have done just now, right? You can see that we always use MPI com world. Maybe look at the program better. Here, MPI com world. Here I don't use MPI com world, but here I use MPI com world. Here I also use MPI com world. What are they? What are these MPI com world? Whenever we communicate using this MPI, remember it's message passing, right? So MPI actually is quite flexible. You can create 1,000 threads, and you can group them into multiple clusters. Okay? Suppose this cluster is to work on certain job, and they need to communicate with one another, right? So we create a channel. Okay, let's put it like a pipe. Okay, and this need to communicate with oneself. We create another channel. Okay, and we create another channel for this cluster and this cluster. So this cluster is going to have multiple processes running, but they need to communicate with one another, right? So we can create a channel, and this channel, if one process sent to this channel, the rest inside this cluster is going to be able to listen to it. That means they communicate with one another, but they are not able to pass that message to this other processor, because this process is listening to this channel, not to this channel, right? So how if I want them all to communicate with one another? So we create one more channel, and this is the default channel, and this is the channel where everybody is listening to, and we give it a name. We call the name as MPI com world. Is that right? Okay, meaning that because everybody is going to listen to this, of course you have to write program to listen to it. How do you write? You do it this way. Okay, we put MPI com world, meaning that it's going to listen to this. Okay, so every channel that is listening to, every process that is listening to this is able to get the message from any one of these processes that is sending to this channel. You understand? Okay? Now, so is there a limitation? Can you only listen to one and you cannot listen to the other? No. You can actually create another channel like this. Okay? So let's say this one P1, P2, P3. This one P4, P5, P6. Now, P1, P2, P3 is going to listen to this channel. Yeah. P4, P5, P6 is going to listen to that channel. Also can. Okay. And P4 and P3 also want to communicate with one another. So they can actually listen to another channel. We can do something like this. Okay? So P4 and P3 can listen to this channel or use this channel, and they can communicate with one another. It doesn't mean that P3 stuck to this channel, no. You can listen to this, you can send to this. You can listen to this, it also can send to this. Okay? And all of them also listen to this and send to this. And we call this default, the default channel, where everybody will be able to communicate with one another using this single channel. Okay? How do we create it? We can create it. I'll show you how to create it. But this one is created by default by the MPI. Okay? So everybody who is going to communicate with one another, they're going to use this channel, the default channel. Is that clear? Now the rest of the channel we have to create ourselves, and then we assign which cluster listen to which channel. Right? Okay. Having said that, let's come back to this. So whenever they do the MPI reduce, so whoever that is working on that particular work, they need to communicate with one another, right? Okay, so in this case, we're not going to create a new one. We're going to use the existing one, which is the MPI combo. So in our MPI reduce, we're going to use this MPI com work here. So that solves the problem. Okay, so right now I don't have this problem anymore. Okay, let's have a look at the count and the type, data type. Okay, what do we do with MPI reduce? Now, what do we do with MPI reduce? Remember, all this process is going to compute all this, right? So it's going to be hard work because why? You have to compute this street, add this street, add this street, and this street, and they are long. And eventually, process 0 is going to find out the result. Okay? Process 1 is going to find out its own partial result. Process 2 is going to find out its own partial result. Process 3 is also going to find out its own partial result. So you've got 4 altogether, right? But then this partial result is partial result of this. We need to add all them together, right? That's why you need this reduction. Right? Reduction means you're going to combine that into one. And who is going to do that? There's going to be one thread that is assigned to do this sum. It's going to take all this and then combine them to give us a result. A single result. Basically, take this, add this, add this, add this. That's why it's sum. And who is going to do this? We have to choose one person. Okay? So we got how many processes? 0 to 3. We can choose any one of them, but we choose 0. The best or the safest person to choose is 0. Because we cannot assume that when we start the time, we will start with any number, right? But we must have at least one process, and that process is 0. Okay? So we choose root to be 0. So this 0 actually have to work also. It's actually a worker. But it itself is also the last person to actually sum all of them or reduce them to one result. Okay? So we're going to assign this as root. Okay? The root. So we're going to tell this MPI reduce, which is this one. Okay? And who is going to do this? Is root number 0. Or the root. Is the process 0. Is going to perform this. That's how we specify who is going to do it. Okay? And all of them are going to communicate using the MPI convert. Right? And what kind of operation that we want to do? We want to do MPI sum. Okay. And what is the name that we're going to use? Is here. It's given down below there. So let's see, what kind of operation that we have? We can find the maximum of all this number. We also can find the minimum of all this number. We also can sum, which is the process that we want to do. We also can find the product, with this, multiply with this, multiply with this, multiply with this, and then the result over here. Of course, this is not product, this is going to be sum. But what I'm trying to show to you here is you can have multiple kind of operation to do. Okay? You have len, law. Len is logical and, law is logical or, ben is bitwise and, bor is bitwise or, and there's a max location. Max location is just like max, except that it returns not the value, but it returns who is the owner of that value, the process ID. Okay, let's say for example, the maximum number is, let's say this compute and it's 1000, this is 2000, this is 3000, 4000. Okay, so the max value is 4000, right? So you put MPI max is going to reduce and find the maximum, and you put the maximum here, which is 3000. Okay? But then if you put MPI max lock, actually its location, is to find out who is the owner of that maximum. The owner is 3, so the value here will be 3 instead of 3000. It will be the 3. Okay? The owner, which is the process that is computing this. Okay? So that is for that. Okay, how about len, law, and ben, bor? Okay, logical and, logical or, bitwise and, bitwise or. Now, logical AND is basically dealing with true false only, right? So you got true, and then you AND with false, let's say for example. What do you get? The result is false. Is that? True is 1, this one is 0, and then it's 0. Okay, or maybe we just look at true and false. So whenever you do this AND or logical operation, we are looking at true and false only. Yeah? And anything that is bigger than 0 is true. Anything that is 0 is false. Okay? So there are only two states. How about band, which is bitwise AND? How does it compare with logical AND? Now, bitwise AND, as the name suggests, is actually doing bitwise ending of the result. Let's say, for example, you have the first result is 1100 or 01. And then you end bitwise AND with 1100. Correct? So bitwise AND basically doing a bitwise, that means bit by bit, ending. So 1 with 1 is 1. 1 with 1 is 1. 0 with 0 is 0. 1 and with 0 is 0. So this is the result. Okay, it's not true or false, it's this bitwise AND. Okay, so the same as bitwise OR and logical OR. Logical OR basically just true or false, but bitwise OR is doing ORing each bit by bit. Okay, that's the difference between these two. The one that we want to choose is sum, basically is this one, MPI sum. So you go to put MPI sum in the operation. Okay, then put here. Okay, in there. Okay, how about the type? The type is the type of value that you put inside it, that you calculate. If this type is integer, then you put integer there. If it is double, then you put double. If float, then you put float. Okay, so it's the type of the data that we are processing. Okay? Now, how about the count? Okay, let's have a look at this picture here so that it's easier to explain. When you do the reduction, for example, in this simple example here, you're reducing this number, and the reduction process is sum. So basically, it's going to take this number plus, and you get 18. Okay? Now, how many items that you will do? One only, right? One out of each. So the count will be 1. Okay? But sometimes you are not going to only do for one. Your data might be in pair. Okay? This process 0 produce a pair. This process also will produce a pair. Okay? And when you do MPI sum, basically you're going to add the pair together. Not pair together, but each of elements in a pair is going to add. Okay? Let's say 5 plus 2 plus 7 plus 4 is going to be 18. The second one is going to be 1, 3, 8, 2 is going to be 14. Okay, so it's a pair also. The result will be a pair. Okay, how many? The count inside this data is 2. Okay, 1 here, 1 here. Okay, and the type of course is integer. We know that it's integer, right? If a floating point, let's say it's double, then it will be double. Okay, so here is 2, so the count will be 2. In our case here, how many? It's only 1, right? Because the process is going to compute, and you're going to compute partial sum, and it's only 1. So you know that this is going to be 1. For our case, it's going to be 1. Right? The type, I believe, is going to be double, and here is going to be 1. Now, let's see how do we use, what is the name that we use? Let's check here, because I don't think it's written there. You can always go to here, and we show you all. Okay, these are all names that you can use. The MPI signed character, MPI unsigned character, short, integer, long, integer, long, unsigned, long. And then you got one character, float, double, long, double, unsigned integer 8, unsigned integer 16. Sorry, this signed is unsigned. Then you got many different types. Okay, we got C Boolean and C complex. The one that we want to use is MPI double. I believe our number is MPI double, right? So you're going to use that. Use this one. Okay? So you're going to put it here. Type MPI double. And how do I know it's double? You look at the program. The program. Okay, you see the result? The result is double. The sum is also double. So you're going to use MPI double. Okay? Okay, the last one. The last one is this. Send and receive. So what are they? Take note that this is the pointer. Pointer, and this is also the pointer. So it's point to the memory of the data. Okay? Okay, we have send and receive. Why? If you look at the MPI reduction, who is the sender? The sender is all this process. Who is going to send the data to be reduced. Okay? Who is the receiver? The receiver is this process here. It happens to be the same process, process 0. So process 0 is going to send to itself. Process 1 is going to send to process 0. Process 2 is going to send to process 0. Process 3 is going to send its own result to process 0. So that it can sum them together and produce a result. Okay? So the send data is going to be this address, the address of the data that you want to send across. Okay? How about the receive data? The receive data is going to be the address of the variable which is going to hold the added value. When you add the value, where do you want to put it? Okay? So we know that this one is going to be the result, the address of the result. And we know also where you're going to put it into the sum. Okay? The name is there. How do I know that? Because if you look here, if you look at the program, all the process is going to find its own result, right? So that will be the send data. And rank 0 is going to receive it after it's summed, receive all this number, and then it will put the value into the sum. It's going to put it in here. Then only compute the pi. Okay, so rank 0 is going to do that, and then rank 0 is going to also compute the pi later on. But it's going to put it into the sum first. So here is the send, here is the receive. Okay? So I already showed to you all. So you should know what to put inside here, inside here, inside here, inside here, inside here, inside here, and inside here. Okay? So you're going to call this MPI reduce. And where do you call it? Call it here. Okay, I put the question mark inside there is the one that I mentioned to you just now. The data that it is supposed to do. Okay? Like that. Okay, next. Next is, first you need to compute the rank, so you need to find the ID, process ID. You should know how to do it, right? Look at the question number 1. Oh, sorry, not question number 1, the previous exercise. And then I also need the size. How do I know the size? The size is the number of process. So the number of process is second line. Okay. So look at the previous exercise up here. Okay. How to find it? Okay, and then here we actually get the time, start the begin time, and then the end time, begin time and end time, yeah. And then you're going to compute the time taken so that it knows how long it takes. Now if you look at the text just right on top of the beginning, is we write down that synchronize all process and get to the beginning. Right? And then down below here, it says synchronize process and get the end time. Okay, maybe you're not aware what is happening there. Okay, let's have a look at the exercise here. It give you some hint here. It asks you to use this tool here. And look at the top here, it says MPI barrier. Okay, this MPI barrier is something to do with the similar like the barrier in OMP as well. Okay, what is the barrier? The barrier is going to be like a gate where everybody is going to reach that point, and it will not open until everybody reach that point. Then only open, allowing the rest to access, to bypass. So that is the use of the barrier. Is that clear? Now, why do we need this barrier here? Let's have a look at the code. When we start the program, right? Remember I mentioned to you that this single program, multiple data. Okay? And all the process is going to run this single program. And everybody is going to be faster than one another, right? They're not going to wait for one another. Some of them will reach here, some of them is still up there. Okay? And then everybody is going to get his own time. Is that true? Get his own time. But it depends on who is faster, right? Is that true? Fair enough? But if you do that, then our timing will be wrong. Because some is faster, some is slow, isn't it? So what we need to do? What we need to do is, we need to create a barrier just before we get the time. We wait for everybody to reach that point first, then it opens, then everybody is going to get the same time. Right? Now the time will be synchronized. Okay, that's why it's called synchronized process. Because we want to allow every other process to reach that point before they get the time. And when they compute this, the same thing, some of them will be fast, some of them will be slow. The faster one will get past this line and get the time. And everybody will have a different time. Not good, right? Because right now, how are we going to compute? We want to make sure that everybody completed first, then only get the time. Now we be accurate. So it's not depending on who is faster. Right now it's going to wait for all. That means you want to make sure that everybody is finished doing this, then that will be the correct time to find the end time. So here we need to put another barrier here, just before this barrier. Since we want to wait for all, once everybody reach that point, you open, and everybody is going to find the last end time. Okay? But then who is going to compute the period? Rank 0. Rank 0, everybody will have the same begin, same end, so no problem. So rank 0 will have the same begin and end as well, as the rest, right? So he's going to represent that means this rank 0 is going to represent all of them by printing out this period. And this period will be the same for all, because we got a barrier. Okay? So I'm going to do only for this, the rest you're going to add it yourself. Okay, so I'm going to use this and paste it in. So I'm going to do it for you, and then the rest you will do it yourself. Okay, so at that barrier, before the start time, that barrier, before the end time. So that when we get the time, everybody is getting the same start time and end time. Right? What you need is, okay, there's something that we're saying, actually is a trick, but I'm not going to trick you. Here is, you need the MPI. Okay, initialize the MPI. Remember, you have to initialize the MPI first before you use any of the MPI functions. So you initialize, you get the ID, because you need the rank here. You get the process number because you need the size here. And then the MPI did, sorry, not without type, but this one MPI reduce, which is this function. Okay? What to put, I will mention here. Result, sum, count is 1, MPI double, MPI sum, root is 0, communicator is MPI combo. Okay? And in fact, the answer is already given down there. Whatever I mentioned to you is here. Yeah? So you just need to put it inside here. I give you, you got only 4 minutes to do it. It's very simple. I've already done all the hard work for you, including explaining all this. What you need to do is just put in the blanks. 1, 2, 3, 4. Only 4. 4 lines of code. The MPI reduce is already given. Look at the data. I mean, look at the document. For the rest, you refer to the program above. This program. What to put here, here, and here. This one, the solution is already inside the document. Look at it, and then put it there. Okay, when you run, use this MPI exact. Use MPI exact. Okay, how many process depends on your depends on you. I suggest that you start with 1, okay, and then with 2, with 3, with 4, with 5, with 6, until 8. That's it. Okay, then you check the timing. You see the timing is going to reduce. At one point, it doesn't reduce anymore. Okay? From there, you also can predict how many cores that is running this process. Okay? Because as a number of the cores that you use, then the faster it's going to run, right? Okay? But then if you don't have enough core, even though you have multiple processors, it's going to be assigned to the same core. Okay, so you will not see any more improvement in the period. Okay, the period will not improve anymore. So from there on, you will know how many cores that is being used in your process. So I suggest you start try all. As you try, make sure that the answer is all the same. The pi here is going to be 3.14 something. Okay? Okay, try now. We got only 2 minutes left. Well, at the same time, I will take the minute. Dinjaman, okay. Ganwei Song, Kama Dashini, Ho Wei Li, Jackson Chatai, Jackson, okay. Lao Yongjin, okay as well. Li Shenhai, Liu Weizhen, Liu Jiayi, Lin Guihan, An Junho, no, not there. Wei Shun, Pan Yu Wen, Samita, Tan Zhonghan, Tan Shenji, Tan Xiuyan, Tan Wenhao, Wang Xinyi, Xinyi, Yi Jiangyue, 신입이 넘기요. 사격가 넘기요. 준호 넘기요. 잭슨. 딩장만. 샤즈니. 샤즈니 here. Okay, do you get the answer? Actually, it's very simple. You just add in whatever that you see there. Append reduction, the answer is already inside the document. Just put it there. Do you get?
Should I put the size also? Size.
Huh? The size is this. It's the process number. Sorry. Yeah, process number. The size of your process. If you put 4, then the size will be 4. Right? So how do you get the size? Look at your program before. Look at this program here. So I ask you to read your code. Because I let the PL go around and ask questionnaire, ask you all. Not this group, maybe some other group. Ask about this course. Do you know what you are learning? The person said, don't know. No idea. No, you have to run it. Go back to it. Right click. MPI exert. Hyphen and then the number of tracks that we have. Oh yeah, it's correct. There's one more. Yeah, it's correct. I can see the answer is correct. Anybody else? Okay, you can leave early actually, it's already over. But anybody else have problem? Or you want to check? None. Okay. Already, okay. Yeah? If you have questions, you can ask, or you can leave it.
네, 그냥 진짜 어려워요. 바이바이.
Sorry, you already got the side. It's a side. You don't have that, you have size. Size.